Very good, thank you. I'd like to thank the organizers for inviting me here. It's my first trip to Israel. I've been to Africa several times, but to Egypt. I've been to Africa several times, but the first time I've actually been to Egypt. I want to talk today about the Africa Biofortified Sorghum project, and it's a project that's been going on a while, but you might ask the question, well, why sorghum? Well, it turns out, why would we be interested in sorghum? Why would we want to worry about biofortifying sorghum? Well, it turns out that sorghum is a staple food for about 300 million people in Africa. It's the 5th most important grain for food use in general. Another thing about sorghum is that its center of origin is in Africa. It's a primary cereal, primarily in arid and semi-arid geographies. And it's particularly important in areas of high temperature, of drought, and of that type of thing. Sorghum is a grain that grows under these adverse conditions reasonably well. It's a good source of energy, but it has very low provitamin A content. It has low iron and zinc bioavailability, primarily because of high levels of phytate, and it has poor protein digestibility that becomes even worse after cooking. Now, these micronutrient type of characteristics have a significant impact on human health, particularly amongst infants and young children. And so what we want to talk about today is what can we do about those particular areas. You know, the thing about sorghum is that for 300 million people in Africa, it is their staple diet. That's the primary food source. If there was any other food source, it would probably help to balance out these micronutrient deficiencies, but it's usually just not the case. So the ABS, or the Africa Biofortified Sorghum Consortium, was established really back in about 2005 with funding from the Bill and Melinda Gates Foundation. There were many organizations involved in this. Most of these were Africa-based. The consortium was coordinated by Africa Harvest, which was an African NGO. It's headquartered down in Nairobi, Kenya. And one of the really important things about this project was, in addition to actually coming up with biofortified sorghum, the other idea was to ensure the technology transfer and capacity building that could be enabled to enable folks in Kenya, in Nigeria, in South Africa, to be able to develop these particular technologies on their own once the funding was over. So much of the capacity building was done in our laboratories at Pioneer Hybrid in the U.S. The outcome of this particular consortium was the achievement of the world's first golden, if I can put that in quotes, sorghum, and the first confined field trial of transgenic sorghum in Africa. Now, the phase 1 ended about a year or so ago, and phase 2 was really picked up by the Howard Buffett Research Foundation, and that was primarily to complete the technology development for this project. There were several key project objectives for the original ABS phase 1. It was really focused on women and children to start with, especially young children. The targeted traits were improve beta carotene, to improve the quantity of beta carotene in sorghum, and also to improve its stability in sorghum, to improve the iron and zinc bioavailability, and to improve protein digestibility. The other notion was to transfer the technology, as I mentioned, and then to start to think about what would the improved product development and delivery systems look like for Africa. So as we moved into phase 2, that is with the funding with the Howard Buffett Foundation, the idea was to complete the technology development and to maintain the relationship with Africa Harvest to make sure that we could continue the confined field trial activities and to maintain project relevancy in Africa. Now, the project was originally designed to really focus on 2 major countries to start with, and that was Kenya and Nigeria. We have Burkina Faso on the map, but they're a little bit behind in where we want to be with them. But nevertheless, we're concentrating right now on Kenya and in Nigeria, primarily because they had biosafety laws in effect that would allow us to eventually conduct these confined field trials of sorghum in the areas of interest. The idea, of course, is that once we're able to deliver, introgress our biotech sorghum, transgenic sorghum, into local varieties, that the material could move out from these countries as a center of origin, going out into other areas that rely upon sorghum as their staple part of people's diets. We divided the phase 2 really into 2 stages, primarily to ensure that we could deliver a product as soon as possible. And the first stage was all about making sure that we could deliver a transgenic sorghum line that would provide 30 to 50% of the RDA, that is the recommended daily allowance for vitamin A for children. And stage 2 was all about then delivering a transgenic construct that would increase iron and zinc bioavailability by 50 and 35% respectively. And then the idea was then to be able to stack that with the genes for beta carotene, and then to stack all of that with genes that we had already identified for protein digestibility improvement that had already been done back in the first part of the project. So one of the things that we needed to do early on was to determine, well, what's our target? You know, we're out here trying to make these improvements when we didn't really know when we started out what's it going to take to be successful. So we actually conducted some ex-ante studies in Burkina Faso actually, and looking at how much sorghum is consumed, what would that have to look like, and what would some of these RDA values have to be. So like I said, we were trying to shoot for vitamin A levels of about 30 to 50% RDA, even after 4 to 6 months of ambient air storage. And so what that means is somewhere around 300 micrograms of a retinol activity unit is what we were looking for to shoot per day. And if we look this out, if we work this out, it turns out for 1 to 3 year old children can consume about 100 grams of sorghum per day. And that means that 100% RDA would be 300 micrograms. You're going to have to excuse me just for a moment. I'm fighting a throat infection. I'm going to start coughing here if I don't do something quickly. So what we want to come up with is about 300 micrograms of retinol activity units per day. Now, unfortunately, for humans, the only way that we can make vitamin A is that we have to get the vitamin A precursors through our diets. The only way we can do it. And unfortunately as well, one unit of precursor does not equal 1 unit of retinol, which is what we actually use to make the vitamin A. And the ratio is somewhere between biofortified cassava, the ratio of conversion of beta carotene to retinol is about 2.8 to 1. For golden rice, it's about 3.8 to 1. And in a maize, through breeding, it's about 6.5 to 1. So we're making the worst case scenario here, assuming that it's going to take 6.5 units of provitamin A, beta carotene that is, in order to equal 1 unit of retinol, which will then goes into figuring the amount of vitamin A that can be produced. So continuing on our chart here, if we were to figure storage just even for 2 months, that would mean that we would have to have about 25 micrograms per gram of beta carotene to start with. The half-life of beta carotene with vitamin E is about 2 months, and the cooking losses are about 20%. So what that means is that what we'd be able to come up with is about 154 micrograms if we were to come up with 25 micrograms per gram to start with, and then that would give us about a 50% RDA. Now you see what happens after even going to 4 months, then we already have dropped to 25%. And these numbers will make sense in just a moment, because I'm going to show you where we are today and the values that we have. Well, unfortunately, I'm going to have to show you the carotenoid biosynthesis pathway and to show some of the enzymes that we're interested in again. And again, I'm going to have to apologize here for just a moment. And this is the primary pathway that we have to deal with. And it's all about moving, producing the geranyl diphosphate, which is the primary molecule that we're going to use to produce both vitamin E and down through this pathway, down to lycopene to produce beta-carotene. And there's several key points along the way here that we're going to try to modify transgenically. And it turns out in sorghum, that's about the only way that we can really increase beta-carotene. It's not the case in maize. In maize, you can actually do it by conventional means, but the variability doesn't seem to exist in sorghum. So the genes that we're going to primarily be involved in are these. There's some key genes here. Phytoene synthase, and we have the CRIT-I, which is the carotene desaturase, the deoxyxylose synthase gene, and then this is the gene that makes the vitamin E, and I'll show you where that's important in just a moment. So our progression through the transgenic buildup here is that we started out with one particular construct that just had 2 of the genes. But what we noticed is that shortly after pollination, we were able to notice that the seeds were visibly yellow, but that yellow went away by the time that those seeds were harvested. So we thought, okay, what we need to do is boost up the amount of beta-carotene. So we did that by introducing the Arabidopsis DXS gene. And by the way, these genes are from maize right here. It's the maize phytoene synthase gene. It was simply worked better than any other one that we could put in. These are both transgenes that we inserted into sorghum by transformation. So when we added the DXS gene, and you notice back on the pathway here, that was really further up on the pathway, and it was really forcing more throughput. That when we did that, then now we noticed a golden color that stayed there even in mature seeds. And we came up with about 10 micrograms per gram. But what we also noticed was that after a period of time under storage, that particular color went away again. So then we thought, all right, one way to perhaps do that is you know that vitamin E is an antioxidant. We thought that maybe by adding vitamin E, we could actually improve the stability. So we did that, and with this particular construct, we're able to improve the stability by 2x actually. And so here you can kind of see these colors. They're not probably don't show up the best, but this is what the color looked like after storage with the construct that had these 1, 2, 3, 4 genes in it. And when you look at a group of genes, you can see that there is a visible difference in coloration. Now we wondered, when we saw this though, the problem is we were still at 10 micrograms. And remember I showed you before that even with 25 micrograms, we're able to, the amount of RDA that we could hit is starting to drop down around 25% or so. So we thought, well, is there anything else that we can do? Well, one of the things that is very important when one's working with transgenes is to come up with single copy inserts. You know, and I think that's been shown earlier in this particular symposia, that multiple copy inserts are nothing but trouble. They don't segregate correctly, they can undergo silencing, and so you really have to be able to work with single copy. But what we noticed here on some of our, and so we screen everything for whether it's multiple copy or single copy. And what we noticed in some of our multi-copy stuff before we got rid of it was that they were, you know, it looked quite a bit darker golden color than our single copy things did. So that told us, if you compare that to the wild type up here, you can see there's really quite a difference. So that told us that we weren't yet to the level of expression where we will be. So what we decided to do was to boost up the expression by inserting the Colorflower Mosaic 35S enhancer region to the promoter that was driving the phytoene synthase. And that's what we have here. This is the beta-caffrin 1 gene from sorghum with the 35S enhancer. And we put that in using different series of promoters. And you can see here that with the line that gave us the 10 micrograms per gram in a homozygous T2, homozygous now T2, that when we compare these T1 seeds, remember T1 seeds was a self of a T0. That means that a fourth of these T1 seeds aren't carrying the transgene at all. Half of them are carrying, the transgene is hemizygous, and for a fourth of them, they are homozygous. And even in those conditions, and these seeds are all blended together because it's just a mixture, it's a cell. And you'll see here that we've got a couple of these lines that are showing fairly high levels of beta-carotene even in that condition. Now we're in the process of taking these out to homozygosity, and we think that when we do that, we are going to be at levels that should be approaching 30 micrograms per gram, which will give us where we want to be in terms of providing the minimum RDA for provitamin A. But it was all about boosting up, again, gene expression of the phytoene synthase gene, Cy1. And if we compare this, by the way, you might wonder, well, what's the level in non-transgenic sorghum? And it's something below a half a microgram per gram. So it's a dramatic improvement over what's natively in sorghum. Now, it turns out that that's only part of the problem. The other part of the issue with beta-carotene in sorghum is that it has a very short half-life. One of the first things we noticed was that after about 4 weeks, we had about a 50% reduction, or 60% reduction in this case, of amount of beta-carotene from when it was just after harvest, stored in ambient air. And then you go out another month, and you're down to very low amounts. Half-life, 50% half-life every 3.5 weeks. And that's when we decided we have to, for one thing, we needed to know why was that happening. So we looked at various reasons. We did the boiling in the water to see if it was an enzymatic thing. And it wasn't enzymatic at all. It was all about exposure to oxygen. So if we kept oxygen out of these seeds, kept these in a sealed bag in a -80 freezer, and then took some of the seeds out and put them in 4 weeks room temperature, you can see we're starting to get a drop off right away. If we put them into pure oxygen for that same period of time, you can see we have a dramatic reduction in the amount of beta-carotene that's available. So that started to tell us that oxidation was a big deal. That's when we decided to go ahead and overexpress vitamin E in the particular line that I had identified earlier as this 203. And when we first did this, we produced the transgenics, and after a time period of storage, you can see right away that we're getting very much a reduction in the amount of degradation going on under normal air, and then under oxygen, pure oxygen, you can see that the level of degradation really was being held fairly stable. So that's when we knew that worrying about vitamin E was going to be very important. It turns out that vitamin E also can have this effect right away once beta-carotene is produced. I may or may not be able to finish this. The enzyme produced, the Cy1 gene, produces an enzyme that actually catalyzes everything. This enzyme comes on very quick after pollination, after about 15 days, and then it drops off dramatically as the beta-carotene starts to come up. And you can see it starts to come up here. That's what this line represents. Now, without the vitamin E, the beta-carotene level makes it to a fairly high level, and then it drops off rapidly. With vitamin E, the vitamin A level never makes it as high as it does in this particular transgenic during the developed maturation stage, but at the end of the day, at maturity, it actually ends up at a higher point. So again, demonstrating to us that vitamin E is a critical component of stabilizing the beta-carotene. And then just one last thing here. When we take the seed and store it after, and just store it, we can look at this, that the half-life without vitamin E is about 3.5 weeks. The half-life with vitamin E is something almost over 7 weeks. So it has just a dramatic difference. So you know, it's always a great thing to be able to do this work in the laboratory, but at the end of the day, of course, these plants don't stay in the laboratory, and they have to get out to the field. So for many years, we've been growing these transgenic sorghum at the different stages at which we've improved them. We started out with one particular set of constructs, slowly but surely went to another set of constructs. We always grew them out in the field. And every time we grew them out, there really wasn't any difference that we could tell between the performance of these transgenic plants with provitamin A and their performance without provitamin A. Because one might think, well, look, you're making this provitamin A, you're making vitamin E, maybe what you're going to do now is impact the productivity, the yield of these sorghum. Of course, that was not going to be an acceptable outcome. So what we did this last year is we actually conducted a series of small plot yield trials, and we looked at the correlation between beta-carotene levels and yield. And what we saw was that it looked like there was a bit of a correlation, but it was almost backwards, as you might think here. And what we're seeing really is the differences that you get from event to event. These are all the same construct that was transformed multiple times. And by multiple times, I may mean that we were looking at well over 100 events here, and we chose 13 of them to grow out. And you can see that even at the higher levels of beta-carotene, that the yield levels, I mean, there really wasn't much difference. There was really no negative correlation anyway between higher levels of beta-carotene and yield. There's also been some concern, well, what about germination? Maybe you're impacting germination effects somehow. And again, when we looked at germination rates, even as the higher levels of beta-carotene occurred, we did not see any particular issues. So we're feeling that we're well on track to getting the levels of beta-carotene that we need to get, and that we'll be able to deliver a transgenic sorghum that will actually make a difference in people's lives relative to vitamin A deficiencies. Now, that's not everything. One of the things about sorghum is it has high levels of phytic acid. And phytic acid serves a real purpose for sorghum. It gives us some protection against different pests, biotic stresses of various kinds. But the problem is that it ties up iron and zinc. And it ties it up in a way such that the human digestive system cannot break it apart. It cannot break the binding between the phytic acid and the iron or zinc, so that iron and zinc is lost to humans. And so what we did was that we downregulated the amount of phytic acid or phytate that was being produced. And we downregulated it 90, 80, and 45% by putting antisense out there, antisense genes for the genes responsible for phytic acid. And then we started to look at, does that have an effect on zinc bioavailability? And we looked at it at two different pHs because the pH in the stomach of a child is different than the pH of the stomach of an adult. But in every case, the homozygote is here, and its null control is here. And you can see that in every case when you compare blue to blue or this purpley to purpley, that there's always a considerable difference between the bioavailability using the CACO2 cell of the transgenic versus the null. So we knew we were on the right track there. Looked at the same situation with iron, and here it turns out that the levels of iron in sorghum in the first place are fairly low. But when you reduce the phytate levels by about 80% again, and if you actually have to spike in a certain amount of iron because otherwise the levels are so low, here's what it looks like with a non-transgenic. And this is the iron absorption as measured by the CACO2 cell. When you add a certain amount of iron back in, you can see that the more that you can reduce the phytate, the more that you can get an increase in absorption, at least as determined by a CACO2 cell. And so again, we knew that we were probably on the right track. There always can be a downside. We always had to look at that. And what we found was that with the two genes that we downregulated, in order to downregulate the amount of phytate, it turns out that it had a negative effect on germination, as we sort of expected that it might. And when you're in with the minoxidil kinase gene, when you downregulate that, you get a range of about 30 to 50% phytate reduction, but that had a dramatic effect on seed weight and germination. When we downregulated the low phytic acid gene, we were able to get considerable reduced amounts of phytate, but in many of the events, we also got reduced T2 seed germination. We didn't see it in the T1. We thought we were home free, but that simply wasn't the case. So we had to make the painful decision at that point to drop this particular approach because we couldn't afford to have an effect on germination. So what are we going to do? Well, the other way to think about it is that what we can do is that we can actually overexpress phytase through the Phy-A gene. And we can actually put a leader sequence on it, and we can dump it into a vacuole in the cell so that we can create these vacuoles in these cells that have the phytase gene in them. And then that way they won't have any impact on germination of the seed. But once the sorghum is processed during the cooking process, those vacuoles will break apart. It will release the phytase. The phytase then will attack the phytate, and then that should then enable an increase in iron and zinc. And those particular experiments are underway right now. We're building those particular constructs. Working with transgenics in Africa, especially working with a plant that has its center of origin in Africa, without a lot of experience in biosafety regulations, can be very challenging. We were very fortunate to be able to work with Africa Harvest, who had good relations with the nascent regulatory groups that were being built in both Nigeria and in Kenya. And we were able to construct confined field trials in both Kenya and in Nigeria, and very successfully grew these transgenic plants there, and are looking forward to our next round of transgenics in these confined field trials for 2013. What we tried to demonstrate is that this type of a process is a continual improvement process. And even though the genes might be the same, we can modify the genes somewhat by use of different promoters in that, but we don't have to go all the way back to the very beginning in terms of trying to get the permits that would be de novo every time we went to do it. So that was part of the approach, and it seems to be working quite well. The one last thing I want to talk about is gene flow. And as was mentioned earlier, gene flow happens. Gene flow has been happening ever since the first cultivated the first cultivated crop was ever grown by a human. Gene flow is happening. The same thing happens with transgenics. But we wanted to address the notion of gene flow relative to our particular modification that we were making. And so we set up a collaboration with the University of Nairobi, Africa Harvest, and USDA researchers in the U.S., and looking at the weediness and fitness of these particular materials that we were developing. It's important to point out that we do not use a herbicide tolerance gene in our selection process. We use phosphomanose isomerase, a gene that comes from another company that we got permission to use in this philanthropic application. And so therefore, the only real genes of consequence that are flowing, if you will, are ones that are impacting the fortification, the biofortification of sorghum in the first place. And as you might expect with these kinds of genes, no surprises so far. There's not any increase in weediness, no increase in the fitness of the outcrosses that there may be. Essentially, this work will be completed at the end of this year. The next round we will complete when we actually develop that final construct, but we'll wait on that until we get that final construct together, and then we'll actually get this work published, primarily driven by Africa Harvest with the University of Nairobi. Summary and conclusions. Several things here. I won't go through all of them. I'll just point out oxidation does cause beta-carotene degradation, and vitamin E can stop that degradation largely. There's really no significant negative correlations that we've observed between beta-carotene and yield or germination rate. Reducing phytate does increase iron and zinc bioavailability, but if you do it from the very beginning, it can negatively impact seed germination. So we have to think a little more cleverly how we're going to reduce phytate, and I've already told you how we might do that. We have already shown that we've improved protein digestibility considerably by suppressing gamma-caffeine expression, and we can suppress it to the point that the digestibility after cooking is better in our transgenics than what you start out with before cooking, and so that is nothing but a positive going forward. The other critical thing here is that strong African partnership. We've established that, we've actively maintained that, and from our perspective, sustained funding for African partners is critical to maintain this continued regulatory involvement and development, and to make sure that our confined field trials continue, and that the whole biosafety network continues to be developed such that this work can be successfully lead to the integration of these materials into local popular varieties that will have an impact on people that rely on sorghum as their primary food source. A lot of people involved in this. I'd just like to mention those, and thank you for your attention.
Thank you very much, Dr. Mark, for your very interesting talk. Actually, I was lucky to be in the United States in 2008 and visited Pioneer, the technology development group at Pioneer, and I witnessed the success and have been done and progress with this project during the phase 1. So to see this success in phase 2, it's very interesting and very optimistic. I wish you very good luck to the success of this project, and I hope to see this in Africa very soon, because we hope to see this sorghum with poor people in Africa. So thank you very much. Now I would like to open the floor for questions, if okay. Doctor.
Thank you very much for this nice presentation. I would be happy to know what arrangements are there for IPR issues later on if African farmers will have to use when you have the product. Given, I'm not quite sure, but some of the issues also in golden rice, for instance. So will African farmers be able to access to this material without any restriction? Thank you.
Yes, please.
One of the things about these philanthropic, there's a couple of philanthropic projects that DuPont Pioneer is involved in, and one of the things about them is that one of our contribution is we are donating the intellectual property associated with this completely. So there is we have no commercial interest, and will not receive any particular compensation for any of this. It's being given to the African farmers as they however they choose to use it. And so the idea is that the genes, the technology that we used will be introgressed into local varieties, and then they will be used as they will be used. Absolutely no tie back at all.
Vivian Moses, Kings and London. I'm very naive with African agriculture. Why are 300 million people so dependent on sorghum? Why don't they vary their diet?
Heat and drought. Heat and drought. And so the areas, if we were to map out where these areas are, they're all sub-Saharan Africa, and it's just about the only thing that will grow, unfortunately. Because in other areas of Africa where sorghum is popular, this nutritional thing is not an issue, because there's other sources of food to balance things off. But in these areas where there's these approximately 300 million people, there's no other choice.
Okay. I have actually two questions. The first is, why you have the budget into two phases? In my thinking, maybe I'm wrong, that you can have cold transformation or whatever you like to have, and that will save time and question is that we may not be very happy with the multiple copies because, as you know, of the co-suppression that might happen due to epigenetic events. What do you think of that?
Right, in terms of multiple copies, no, we stay away from multiple copies. We avoid it at all costs. So I was just showing you the multiple copy thing there, as that was what gave us the hint that we needed to boost the expression of the genes that we were working with. And the multiple copy thing happened to do that for us, but we knew that we couldn't rely upon multiple copies. It's just, because you're exactly right, it leads to co-suppression, it leads to improper segregation, probably later on it would get silenced and turn off, and so we avoid that at the plex. I was just using that as an example that was telling us that we needed to do something to boost the expression, because if we boosted expression, we could get more beta carotene. So that was with the multiple copy. What? Oh, and the other thing about the two phases, I'm assuming you mean the two stages that we had broken into in terms of improving vitamin A first and then reducing phytate, iron and zinc. So what we thought there is that we were once we realized that our initial approach to down-regulating phytic acid was not going to be as straightforward as we thought it was going to be. In other words, it had the negative effects. We realized that we can deliver the provitamin A probably a few years sooner than we could with the added on to the reduced phytate. And we just thought, you know, as critical as the problem is, when it comes to vitamin A deficiencies, especially amongst infants and young children, I mean, once those deficiencies, once they've experienced those deficiencies, it's not fixable. And so we just decided that, you know, we can deliver this almost, we expect to be able to introgress this into local African varieties about in the year of 2015. And it would probably be a little bit later than that for the phytate. And so we just decided that it would be worthwhile to go that route, because that way we can show that we can do what we said we could do, we can get it started, we can get it down through the process, and then later we would, and not much later, but a little later, we'd be able to stack it with the phytate. But all those things we just thought would add too much time, and we just didn't want to expose any more people to this than had to be. So that was really the reason. We're trying to focus, deliver, and then develop the other, and then add it on to it.